So we have the derivation of Rodrigues formula for Legendre polynomials. Our topic here is the uh, Rodrigues formulas for Legendre, Hermite, and Laguerre's polynomials with Mathematica simulations. We have first derived the Rodrigues formula. Rodrigues formula is a compact formula used to generate certain important families of functions. Most commonly are orthogonal polynomials like Legendre, Hermite, and Laguerre, and in another context, rotation matrices in 3D. So we have the most common meaning in mathematics courses is the one of orthogonal polynomials, especially Legendre polynomials. So we have the Rodrigues formula for orthogonal polynomials. So in general, so the Rodrigues formulas is also known as the orthogonal polynomials. In general form, Rodrigues formula is given by these equations. 1 over 2 to the n factorial times the n derivative of x squared minus 1 raised to the n. So this formula defines the Legendre polynomials. Uh, so what each part means. So we have n here the degree of the polynomial. Then we have the n derivative with respect to x here. Then we have the simple base function that gets differentiated repeatedly here. So x squared minus 1 raised to the n. Then we have a normalized factor, so the polynomial has standard scaling. So instead of computing Legendre polynomial recursively, you can generate them directly by differentiating. So let's have some first examples to understand the theory behind the Rodrigues formula. So this is the Rodrigues formula, or also known as the Legendre polynomials. So at n equal to 0 here, so we substitute here in the Rodrigues formula. If n equal to 0, so 1 over 2 0 times 0 factorial, then n equal to 0 here, so this becomes 1. So this becomes 1, n equal to 0. Then just write the given here, so there is no derivative here. That is because n here is equal to 0, so that is equal to 1. If n is equal to 1, so by substitution here, this is equal to 1 half. Then we have the first derivative of x squared minus 1. So n equal to 1, so this is equal to x. So if n equal to 2 here, so we substitute here. So this is equal to 1 over 2 squared times 2 equal to 1, this is 1 over 8. Then the second derivative of x squared minus 1. So we simplify here, we have 1 half of x squared minus 1. So why Rodrigues formula is important? So it gives closed form definitions of orthogonal polynomials. It helps prove orthogonality properties. This is used in solving differential equations, especially in physics. Appears in mechanics, electrostatics, and wave equations. So we have the general Rodrigues formula here. So for many orthogonal polynomials, the formula has this form. So we have W of x. It's a weight functions, and sigma of x, it is a polynomial of degree less than or equal to 2. Now we have another meaning of Rodrigues formula. There is also a version of the rotation here. So Rodrigues rotation formula. So in vector calculus and 3D geometry, Rodrigues formula also refers to these equations. So we have, this is the rotated vector. So we have the given vector here times the cosine of angle. Then the cross product of k and v here. Our k here is the axis of rotations. You multiply by the sine of the angle theta plus k times the dot product of k and v times 1 minus cosine of the angle. So k here is the axis of rotation and v here is the given vector. So this rotates a vector v by angle theta about this k. We have the numerical example. Numerical examples, general Rodrigues formula, orthogonal polynomials. So the general Rodrigues formula is given by this equations, then different choices of Wx and sigma of x produce a different orthogonal polynomials. So we have the example here, Legendre polynomials. So we have the given here, W of x equal to 1, and we have the sigma of x equal to 1 is x squared. So these are the given. So if n equal to 2 here, so we have the beta of x. So by substitution here in the Rodrigues formula. So this is our answer here. And the full Rodrigues formula for Legendre polynomial is given by this formula. So let's further simplify this, x squared minus 1 to the second power. And the second derivative here, so the second derivative is 12x squared minus 4. So by simplification, that is 1/2 of 3x squared minus 1. So for the numerical evaluation here at x equal to 0.5 here. So by substitution here, x equal to 0.5. So this 1/2 of negative 0.25 equal to negative 0.125. We have also another interesting polynomial is the Hermite polynomials here. So for example, our given here, W of x equal to into negative x squared and sigma of x equal to 1. So this is the Rodrigues formula for the Hermite polynomials. Negative 1 raised to the n e to the negative x squared times the n derivative of e to the negative x squared. And by using the Rodrigues formula for the Hermite polynomial, so let's have the second derivative since n is equal to 2, we have the second derivative of e to the negative x squared. So that is 4x squared minus 2 times e to the negative x squared. So the Rodrigues formula for the Hermite polynomial is equal to 4x squared minus 2. Now we have the numerical evaluation at x equal to 1. So the Hermite polynomial here is by substitution here, 4 times 1 squared minus 2, so that's equal to 2.